Hi everyone, welcome back from the break. So in the last segment of lecture, we talked about multivariable functions. So we talked about functions generally, they just map something to something else. But we also specified and talked about these functions that map Rn, so several different real variables to a single real variable. And one of the things we can do with that is we might ask, what is a derivative for these more complicated functions? So in order to answer that, we first need to go back to what is a derivative for an ordinary function. So a derivative measures the rate of change of a function as the variable it depends on changes. So for example, if you have a function f from r to r, so an ordinary function like you saw in your last calculus class, then df dx, df by dx is equal to, sometimes also called f prime, measures how quickly f changes when x changes. Note that f prime is also a function from r to r because f prime of x is a real number, or generally a real number. So let's give a quick example of this. Let's use the parabola, which is a very nice non-trivial function. F of x is equal to x squared. So then f prime of x is equal to 2x. And so you might have like f prime of 1 is equal to 2. And if we draw this out, you guys have seen this before, but let's just go ahead and draw this out. Let's see if I can draw a slightly better parabola this time. So then at the point 1, 1, so let's say that's the point 1, 1, then you have a tangent line here. So the tangent line has slope equal to f prime of x is equal to 2x. So tangent slope at point 1, 1 is 2. Okay, so this is just a brief review of like basic calculus. So it's just measuring rates of change. But now, what happens when you have a multivariable function? So what we can do is you can measure the rate of change of the function with respect to each variable independently. You have an x variable and you have a y variable. You can ask how the function f changes as the x variable gets bigger or as the y variable gets bigger. And so this is how we define something we call a partial derivative. So this is, each of these is only one part of a bigger derivative in some sense, but it's measuring how it changes as one variable changes, but the other one stays the same. So if you're thinking about the playing as you just walk along the x-axis, but not along the y-axis direction. Similarly, the partial derivative del f by del y measures how quickly f changes when y changes, but x is a fixed constant. And note that this is from r squared to r, the derivative still takes an input, a pair x, y, and outputs a single number. Special note, so this is a pronunciation note. So we have this weird squiggly D symbol, right? And people read this a number of different ways, and so you'll hear me saying a number of different things. Hopefully it'll be clear from context. If it isn't, just ask in chat. So you can read this a couple different ways. Some people say del f by del x. Some people say del f over del x. Some people just say del f del x. Often it's a little bit less ambiguous if you say the partial of f with respect to x. And sometimes people even just say df dx if it's unambiguous. Although you have to remember that df dx also often refers to just the ordinary derivative for a single variable function. So hopefully that's clear. But now what does this mean? And one way to think about this is, in the previous example, we wanted to look at these tangent lines, right? So we're looking at the tangent line, and we're looking at the slope of the tangent line, and that was the derivative. So in this case, we might look instead at the tangent plane. So if you have some figure, so here I've taken, well, the natural analog of x squared, which is just f of x, y is equal to x squared plus y squared. And you have this figure here. If you go to the link below, that is also, I've also shown it, so you can rotate it around to see. Actually, let me just do that right now. So this is this sorry, that is the wrong one. So this one here, if you rotate it around, you'll see that we have the x squared plus y squared thing here, and then I've drawn out the tangent plane and two tangent lines. So note that every line in the plane that goes through that point is tangent to it. Which is why we have an entire tangent plane. Let me go back to my PowerPoint. So basically what we're saying here is that the partial derivative gives you the tangent slope in a particular direction. So the tangent slope at the point 1, 0, 1, which is the point I have here, depends on which direction we're going. Direction we are going. So in the x-axis direction, the slope is 2. And in the y-axis direction, slope is 0. Yeah. And so here we have two different directions, and then what we're asking for is we're asking for our slope in each of the different tangent directions, and that gives us our partial derivatives. We have a question in chat: is df dx written the same for a single? I don't quite understand the question. Do you mind clarifying? So df dx for a single variable function, you can also write df dx, of course. Yeah, for a single derivative, you can write df dx using the ordinary d's because it's just a single variable function. For multivariable functions, there is a special meaning for the ordinary d, which we're not going to talk about too much. But when we talk about these partial derivatives, so derivatives in a single direction, then you use the squiggly d. Yeah, so the d's look different, which is one of the. It's sort of like how you guys know that we have that weird integral symbol, right? The weird integral symbol is actually just a stylized s for summation, but we've written it in a weird way, and then mathematicians are like, oh, look, it's a new symbol. We did the same thing with d's. Okay, so now let's go on to, we've talked about sort of the intuition behind these partial derivatives. Let's go on and talk a little bit about a formal definition of partial derivatives. So recall, if you just have a single variable function, then z is equal to f of x, which is a single one variable function, then dz dx or df dx is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. So this is the formal definition using limits, and you can. So this is the formal part of calculus, which I'm not going to expect you to know too much of. Often we also write this as f prime. Okay, so there are a number of different ways of writing this, but this is just an ordinary derivative, which you guys learned in A29 or whichever calculus 1 class you took. But now, when you have a two-variable function, then you have two different partial derivatives, because you can take the derivative with respect to x or the derivative with respect to y. So you have partial f partial x, which is the limit as you hold y constant. So if you look here, the y part here is held constant, so that doesn't change. But then you're changing the amount of x by this h, and taking that limit as h goes to 0. So this here, we also sometimes label this as f sub x, because it's the derivative in the x direction. You can't use f prime because we don't know which direction we're going when you just use a prime, because we have several different directions. And similarly, here we're holding x constant, and you're taking the derivative with respect to y. And now this generalizes in the natural way to n-variable functions, where you just treat all the other variables as constant. And so now computing it is relatively simple if you know how to take derivatives, because you just treat all the other variables as constants and apply the normal derivative rules. So let's give a couple examples of this. So let's say we had f of xy is equal to x squared plus y squared. Well, then we have del f by del x at the point xy. So note that this here is just specifying that it is a function of x and y. Give me a moment. Let me finish my thought here. So this is equal to del by del x of x squared plus y squared, since that's f of xy. And note that here in this example, this y is a constant. And because this y is a constant, the derivative of a constant goes to 0. And therefore, this is equal to 2x. And we can do the same thing by del f by del y of xy is equal to del by del y of x squared plus y squared. And here, we instead have this x as a constant. And so this is equal to 2y. And note that if you plug these things in, we know that f of 1, 0 is equal to 1, del f by del x of 1, 0. is equal to 2, and del f by del y of 1, 0 is equal to 0, which corresponds precisely with the tangent slopes of this figure at that point. Let's see, there was another question, which is, could we write it as f prime x, f prime y? People don't write it that way, so I suggest you don't. Like, these are all just conventions, right? So these are all just conventional notations. If you write that, people might know what you mean, but they probably won't. So I will generally try to write it as with this full del f by del x, because that makes it very obvious that we're doing these partial derivatives. So these, yes, exactly. So these find the tangent lines in the x and y directions. That's precisely what the partial derivatives do. Because we had, so you have all these different tangent lines, right? Because you have this entire tangent plane. And what you're asking is, well, if you want to measure a slope, you need to first define a direction. And so if you define the positive x direction, then you're measuring the tangent line in that direction, which is this line going. So this line here has slope del f by del x is equal, at that point, which is equal to 2. And the other line has slope del f by del y. Okay. So that is how we compute them. Let me give another example before I make you guys try it out. So let's give a slightly more complicated example. So f of xy is equal to x squared plus 2xy squared plus y cubed. So now, how do we figure this out? So, well, we have del f by del x of xy. Note that often, so I'm writing it as a function of xy because because just to drive home the point that it's a two-variable function, but very, very often, especially later on, you'll see this as just del f by del x. So you don't always write down the fact that it's a function. So this is del by del x of, you can of course take the derivative of each part individually. So I'm going to split this up. So this is x squared plus del by del x of 2xy squared plus del by del x of y cubed. Right? Because of course it's derivatives, and so you can split it up. Oh, we have a question. It is x in both the positive and negative direction. So that's actually a very good question, Sam. So this is in the positive x direction. So now whenever you take so that's not quite true. So it's the slope of the line. If you think about the number line, when you think about a number line and you think about slope, you always specify going in the positive direction. So it's rise over run as you go in the positive direction, right? And so that's the same for these partial derivatives. It's rise over run as you go in the positive x direction or the positive y direction. If you go in the negative direction, well, obviously it's going to go down instead. So just like normal derivatives. But anyway, so here, well, this here is equal to 2x plus 2y squared plus 0, because we're setting y as a constant. So this is equal to 2x plus 2y squared. So treat y as a constant. Oh, we have a question. It had both positive and negative tangent lines. Oh, so if you're going back to this example, it's the tangent line is just a single line. It goes both forward and backward when you're past the point, and so it is the slope of that tangent line. Yes, but if you what we're asking is as you're going in the what it describes is as you're going in the x direction in the positive, do you go how much up or down do you go? If you go in the negative direction, it's obviously going to go down instead. Sorry, let me switch back to this example. Hopefully that answers your question. If not, I can expand a little bit in the break. But yeah, so that was the del x by del x. And we can also do del f by del y. So this is, of course, equal to del f by del y of xy, which is equal to del by del y of x squared plus del by del y of 2xy squared plus del by del y of y cubed. Oh, sorry, bad brackets. So this is equal to 0 because x is constant here, plus 4xy plus 3y squared is equal to 4xy plus 3y squared. Since treat x as a constant. Okay, so now I'm going to have you all try it out, per usual. So let's say we have this function here, and I'm going to ask you to compute del f by del x. Let me reset. Oh, I already reset my chat. Okay. While I'm waiting for you guys to figure that out, if you think about it, when you think about an ordinary derivative, right, it's saying as you go in the positive direction, not in the negative direction. Because if you go in the negative direction, obviously you're going down if you go up in the positive direction. So it's exactly flipped. But it is still the slope of the same tangent line, because the tangent line is the same for going in the positive and negative directions. Okay, so it looks like we have some number of replies that are showing up in chat. Looks like everyone is saying B. Okay, so let's compute this. So this is equal to 6xy plus y squared. So yes, it is B because you're treating y as a constant. And you're taking the derivative with respect to x. Okay, so let's try another one. Okay, so now you guys can... What is df dy? Well, it looks like people have already started computing this. Okay, yes. So this is indeed equal to 3x squared because you're treating x as a constant and you're just dividing out dy is equal to 1 plus 2xy. So this is indeed C. Okay, and let's keep on going. So let's have a different one. And again, we're going to go through the same things. So I want you to compute dg dx. And I will also, in a moment, want you to compute g sub y, and then later the w dz. But we'll do that in a moment. So, oh, sorry, did I reset? I don't know if I reset, but it looks like everyone's answering anyway, so that's fine. So, okay, oh, I did reset. So, yes, this is equal to 0 because there is no x component. And let me reset, and let's do the next one. So when you compute with respect to y, what you end up getting is 10y plus 2z. And so, okay, yep, the chat is way ahead of me. And let's do the last one. So for del w del x, well, what is this equal to? Let's see. Okay, so we have a couple of different answers. So let's look through this a little bit more carefully. So remember, w is a function of x, y, and z. So it's the same as g. So this is equal to the same thing as del g by del z, which is equal to, well, 5y squared doesn't have a z component, so it just is a constant, goes to 0. And this is just equal to 2y. And so it's equal to, so B was the correct answer here. Okay, do you see what's going on? Basically, del w by del z is the same as del g by del z. And you treat x and y as both constants. And when you treat x and y as both constants, 5y squared goes to 0, and 2yz goes to just 2y. Okay, let me try, let's give a couple more. So let's evaluate at a point. So compute the f sub y at the point 1, 2. And let me reset before you guys reply. So remember, these are functions, so you can evaluate them as functions. Okay, looks like we're starting to get some answers in. Good. So, yeah, so basically this is measuring the slope as you go in the y direction at the point 1, 2 of this of the function f. And that's equal to 3 plus 4, which is equal to 7. And one last one. So, come on, there. Okay, so we have a number of different replies, mostly B's. Yep. So this is equal to 2 because you're just plugging in 0 for x, 1 for y, and 2 for z, and you end up getting wait, what happened here? Del w by del z is just 2y, so 2 times 1 is just 2. Yep. Okay. So we've can you re-explain the last one? I didn't understand. Yes, I can. So we had this equation here, right? So this is del w by del z. So this here is some function. I'm going to call it alpha of x, y, z is equal to 2y. Okay? And then you're plugging in 0 for x, 1 for y, and 2 for z. But of course, you don't have any x or z, and so that's just equal to 2 times 1, which is equal to 2. Okay, so let's go on to the next topic. So what about other directions? So remember, we had an entire tangent plane, and we only asked about the x and y directions. So del f del x says how fast f grows in the x direction. Del f del y says how fast f grows in the y direction. And now, something that's a little bit more advanced, which you may see in your physics classes, but we're not going to cover on quiz 3. Or, I mean, if we do, it's going to be very carefully explained. So this is a slightly more advanced topic. So given any direction, so note that you can specify a direction in the xy plane by just choosing 2 different coordinates, right? And so that specifies the direction. You need to normalize it so that the direction size of the vector is equal to 1. You can compute how quickly f grows in any direction u, that's defined by this vector, by computing this matrix product where you've taken your del f del x and del f del y and put them in a single row vector. But what does normalize mean? Normalize means that you need the, in this case, it means that you need the length of the vector to be 1. So if you think about like the direction, you want your basic x direction to have unit length. So if you think back to our standard basis vectors, they all had length 1, right? And so this is why this is a slightly more advanced topic. So I don't expect you to understand all of this yet, but I just had to put this in there to make this the formulas work. So you can compute how quickly f grows in any direction by using this matrix product. And we give a special name to this particular matrix. Some of you may have seen it before. This is the gradient of f. And you can think of the gradient. So remember, we talked about all these things as partial derivatives, right? So what are they parts of? And you can think of this gradient matrix, this vector, a row vector, as in some ways the entire derivative. So this combines all the different parts of the derivative and tells you, as you go in any direction, how does f grow? Any questions on that? So some of you may have seen this in your physics classes. If you haven't yet, you probably will, since gradients are very important in physics. But this is basically the idea of we specify 2 different directions for this growth, this partial derivative, but you could, in theory, specify the derivative in any direction. And this matrix tells you how to compute the derivative in any direction. Okay, the reason I put this on here, though, is because it makes it a little bit easier to explain something we're going to cover, which is this thing called a Jacobian matrix, which you may have also seen. When you say length 1, doesn't mean that, oh, no. Let me go back and let me explain this a little bit more. So let's just say that we had a 2D plane. This thing has length 1, right? So this vector here has length 1. This vector here also has length 1. But this vector here can also have length 1 if it's on the unit circle. So when we say that it has length 1, we mean that the length of the line as a distance from the origin is 1. And this gets a little bit more complicated, and I don't want to get into it right now. Feel free to ask me later. But basically, it has to do with the length of the vector. And the length of the vector is something you can measure by taking x squared, by taking the square root of the squared products. So the gradient is like the derivative in both directions. The gradient is like the derivative in any direction. You combine these 2 directions, and then when you multiply it by a direction vector, it gives you the gradient in any direction. Yeah. So if you think about it, if you have the ordinary vector here, so remember this vector here is the vector 1, 0. So if you multiply df, dx, df, dy by the vector 1, 0, you just end up getting df, dx again. So in the x direction, you multiply by the vector 1, 0. In the y direction, you multiply by the vector 0, 1. And by any other direction, you can still multiply by that direction, and you get the gradient, the derivative in that direction. Like I said, this is a somewhat more advanced topic. I don't expect you to know it super well, but it is useful to understand basically why we call these partial derivatives, because they're part of this bigger derivative object that tells you how the derivative in any direction. Okay, so moving on from that, we have something called a Jacobian matrix. And we've been talking about functions from R2 to R, right? So what happens if you think about a function from a point in the plane to a point in the plane? So from r squared to r squared. These are a lot more complicated because now you can't draw them as some surface in 3D, and so they're really hard to visualize. But these are still valid functions because you're taking a point and you're specifying some other point in the plane. And so you can write this function h of xy because it puts you into a different point. You can write it as two different functions, f and g, for each of the two different coordinates. So you can think of this as a function that has two different functions embedded in it. Two different R2 to R functions embedded in it. So now you might ask, what is the derivative? Like, what does it mean to have a derivative of a function from R2 to R2? Well, then the Jacobian matrix of H, or the pair of functions f and g, is given by these two gradients together. So you're looking at the gradients of both of these two functions f and g, and that gives you this bigger thing, which is, in some sense, the higher dimensional analog of a derivative, and it tells you how the output of a function, which is a vector, changes as you go in a particular direction. This gets a little bit complicated, but we do need to know this because this matrix actually ends up being super important for understanding the behavior of a system. So later on, we'll have to compute the eigenvalues of this matrix, and that'll tell you something important about the differential system. And the intuition here is that what this Jacobian matrix tells you for a particular point how the output of that changes as you go in some direction. But of course, because the original function gave you a vector as an output, the Jacobian matrix here gives you another vector, a difference vector, as an output instead of just a number. Okay, so let's give an example of this. So if we have some function, let's give a concrete function. Let's say h of xy is equal to some set of functions f of x, y, g of xy, which is equal to, let's say, 2x minus 3y cubed and 3xy cubed. Then the Jacobian matrix, J, is going to be equal to del f by del x, del f by del y, so the gradient of the f function, and del g by del x, del g by del y, so the gradient of the g function. And this is going to be equal to 2 minus 6y, 3y squared, 3y cubed, and 9xy squared. Okay, so this is a matrix, and this is, in fact, so you can think of the gradient as the total derivative of a function from r squared to r, because it combines together all the partial derivatives. And you can think of the Jacobian as the total derivative of f from r squared to r squared, because it combines together all the partial derivatives of this Jacobian, of this h function. Okay, so this is why we call the other derivatives partial derivatives, because they're parts of this bigger derivative object. So derivative is no longer a number anymore. It's this matrix instead. Any questions there before we move on to the next topic? Okay, so this is a lot that I'm throwing at you, and the basic idea is when you have these multivariable functions, when you start taking derivatives, you can take derivatives in a particular direction, and that gives you something that looks like your ordinary derivative. But if you just take the derivatives in general, you end up with these vectors and matrices instead, which is the reason why we had to learn linear algebra last week. But now, these are just the first derivatives. So, are there higher derivatives? And the answer is yes. You can take a derivative multiple times. You can also take a partial derivative multiple times. So if you have some function, we're going back to a two-variable function from R2 to R, and you can define del squared f by del x squared, or sometimes you write it fxx, which is taking the partial derivative by x twice. Or you can do del squared f by del y del x, which is actually equal, note, be careful, this ordering here and this ordering is not actually the same. Because what this is saying is you're taking the partial derivative with respect to x first, and then the partial derivative with respect to y. Oh, let me erase that so that it doesn't use up my space. You can also take the partial derivative of y first, and then the partial derivative with respect to x. Or you can take the partial derivative with respect to y twice. Okay? So this is just what you'd expect. You're just doing one partial derivative and then doing it again on the function that comes out of it. So let's give an example. Let's see. So we have f of xy is equal to some complicated function that I wrote out. So if you want del f by del x, that's equal to, well, x cubed y squared, when you take the derivative with respect to x, that's going to be 3x squared y squared. Y sine x, well, that's going to be plus y cosine x, because that's the derivative of sine is a cosine, plus e to the y. Okay? And we also have del f by del y, which is going to be equal to 2 times x cubed y plus sine x plus x e to the y, since the derivative of an exponential is just the same thing. Okay? So we do that. We set the other variable constant, and we take the derivative as normal. And now we can do it again if we want to get the partial derivatives. So we have del squared f by del x squared. Take the derivative again. What do we get? We get 6x y squared. And this is minus y sine x. And e to the y, that doesn't have an x component, so it's a constant, so it goes to 0. We can do the same thing. So let's take del squared f, and let's do del y first, and then we'll do del x. Okay? So this is just the derivative of this thing up here with respect to x as well. And what that's going to give us is 6x squared y plus cosine x plus e to the y. And we can take the partial derivatives with respect to y again. So that gives us del squared f del y del x. So again, we're starting from there. So this is going to be equal to 6x squared y plus cosine of x, because the derivative with respect to y is just 1, of y is just 1, plus e to the y. And we can do the same thing over here. So del squared f del y squared is going to be equal to 6x squared plus e to the y. Okay, so you might have noticed something as I was writing that out, which is that these two happen to be equal. This is not always true, but it is usually true that for most nice functions, and by nice functions I mean basically nearly any function you're going to encounter in mathematical biology is nice. And so it's usually true that the derivative of, if you take the derivative with x first, and then the partial derivative with respect to y, that's the same as taking the partial derivative with respect to y, and then the partial derivative with respect to x. This is not always true, but it will often be true, and and for most functions that you do, this will turn out to be the case. Okay, well, let's try it out. So I have a bunch of different partial derivatives, including second-order partial derivatives, and I want you to tell me which of these it's. So let's start with the top one first. So the very first one, del f by del x. What does this equal to? So let's here, you're just taking the derivative with respect to x, and so this is 2x y squared plus 4y. And so, oh, okay, yep, it looks like we have a lot of responses coming in. Yes, it is indeed D. Let's reset. And let's say the next one. Okay, so it looks like you guys are getting very comfortable with taking these partial derivatives. So yes, that is indeed 2x squared y plus 4x. Let me reset again. So what's this next one? So if you take del squared f by del x squared, well, you just take this thing here, and you take the partial derivative with respect to x, and what you end up getting is 2y squared. So that is indeed, looks like people are, okay, good. People have been replying C. The thing just didn't update. Okay, and let's do the next one. So I'm resetting again. So what happens if you take that and take the derivative with respect to y? Well, then that's equal. So we have, okay, have a bunch of answers. It looks like everyone's applying E. So yes, this is indeed 4xy plus 4. Okay, I'm about to reset again. What about the next one? Okay, looks like I should have put this as a different one in a different order, but yes, it is indeed still E. So this is also still 4xy plus 4. And if you want to do the very last one, well, there's only one answer left that I haven't done. But if you take the very last one, you need to, what you end up getting is you end up getting just 2x squared. And that is indeed A, as people are replying in chat. Okay, so taking partial derivatives, it's not hard. You just apply the same derivative rules, and you just have to remember that you set all the other variables equal to a constant. Now, I am going to introduce a couple slightly advanced concepts. So this is going to show up in on Friday's lecture, which is why I'm introducing it now. But there is something called a Hessian matrix. So, oh, sorry, too fast for you. But yeah, so basically, you just need to do all different partial derivatives, and this is why you need to get practice at doing derivatives as well. So I'm going to introduce a Hessian matrix. So we had the total first derivatives, right? So those are the gradients and the Jacobian matrix. The Hessian matrix corresponds to a second derivative of a function from R2 to R. So let me write this out a little bit, and I'll show you sort of what I mean. So let's say we have a function f of xy, which is a function from R squared to R. Oh, we have a question in chat. Are next week's topics also in Chapter 7? So next week's topics are... The book doesn't go into enough detail on next week's topics. So some of it is in Chapter 7. Some of it I will be constructing from outside resources. So they're not all in Chapter 7, but some fraction of them are. And we'll get into that later. But anyway, so let's say we have some function from R squared to R. Well, we had this idea of this gradient, right? This gradient, which is equal to del f by del x, del f by del y, which is roughly speaking the first total derivative. Okay? So now, you can think of this function. You can think of del f as a function del f from R squared to R squared, right? So then you can think about the Jacobian of del f, which is equal to the Jacobian of del f del x, these two functions, and del f del y. And when you take that Jacobian of this gradient, then what you get is this complicated matrix, del squared f del x squared, del squared f del x, del y del x, del squared f del x del y, and del squared f del y squared. And this thing is equal to the Hessian matrix, and this corresponds to the second derivative. Oh, I didn't need to write all that out because I had it all typed out. Oops. Anyway, so this will become super important because remember, there are certain types of things in one single variable functions where you need to find the second derivative to know if something is concave up or concave down. And so if you want to know if a function, a multivariable function, is concave up or concave down, you also need to use this second total derivative. And so this Hessian matrix will play an important role in Friday's lecture. And I am going to take another brief break now. And after this brief break, we'll come back and talk about multivariable integration instead. So I will see you after the, let's say, a 5-minute break. So I'm going to stop recording now.